Let's look at an application of the derivative. If a rock is thrown upward on the moon with a velocity of 10 meters per second, its height after 10 seconds is given by the function h of t equals negative 1.62 t squared plus 10t. And what we're to do is find the velocity of the rock after 1 second. So let's think about velocity for a moment. Velocity is represented by a change in distance over a change in time. And if we look at the derivative of our function here, so the limit as delta t goes to 0 of h of t naught, so a specific time, plus delta t minus h of t naught over delta t, which would be h prime at t naught. If I focus on the units here as I'm doing this limit, notice that we will end up with a change in distance over a change in time, which is a velocity. So what we can say is that the velocity at time t naught is the same as the derivative of h at t naught. So when we're asked to find the velocity of the rock after 1 second, our velocity after 1 second is going to be the same as h prime at 1. So let's go ahead and find the velocity of the rock after 1 second. So this is going to equal the limit as delta t goes to 0 of h of 1 plus delta t minus h of 1 over delta t, which is equal to the limit as delta t goes to 0 of negative 1.62 1 plus delta t squared plus 10 times 1 plus delta t minus negative 1.62 times 1 squared plus 10 times 1, all over delta t. Okay, so continuing on, this is equal to the limit as delta t goes to 0. We'll have negative 1.62, squaring 1 plus delta t, we get 1 plus 2 delta t plus delta t squared. Distributing the 10 into the 1 plus delta t, we get plus 10 plus 10 delta t minus, and then doing the arithmetic for negative 1.62 plus 10, we get 8.38 all over delta t. Now we're going to distribute the negative 1.62. So we'll get the limit as delta t goes to 0. Negative 1.62 plus, actually that should be a minus, 3.24 delta t minus 1.62 delta t squared plus 10 delta t minus 8.38 all over delta t. Now, as I look to simplify my numerator, this negative 1.62 and this negative 8.38 sum to negative 10. So this is negative 10, and we have a plus 10, so those will sum to 0. So we have the limit as delta t goes to 0. We have negative 3.4 delta t and a plus 10 delta t. So I can add those together and I would get 6.76 delta t minus 1.62 delta t squared all over delta t. Now we can factor out a delta t in our numerator. So we have the limit as delta t goes to 0 of delta t times 6.76 minus 1.62 delta t all over delta t. At this point, the delta t's can divide out, and I'm ready to consider how my function 6.76 minus 1.62 delta t behaves as delta t goes to 0. So, as delta t goes to 0, 6.76 minus 1.62 goes to 6.76 minus 1.62 times 0, or 6.76. What are my units? Well, the units associated with the numerator in this ratio were meters, and the units associated with the denominator in this ratio were seconds. So the units for my 6.76 are meters per second. So always a best practice to answer a question with a complete sentence, particularly in the case of application problems. So we could say the velocity of the rock after 1 second is 6.76 meters per second. That really closes the loop and reminds us what the mathematical task we were completing was supposed to accomplish. Now let's consider, rather than the velocity of the rock when after 1 second, the velocity of the rock at a time, let's call it A, then we would have the velocity at time A would be the derivative of the height at time A, which would be the limit as delta t goes to 0 of h of A plus delta t minus h of A over delta t. So notice this is quite similar to the example we just did, with the difference being in this instance, rather than t being 1, we're allowing t to be some time, A, doesn't matter. So let's see how this plays out where we have a generic value for time rather than t equal to 1 second. So we've got the limit as delta t approaches 0 of negative 1.62 times A plus delta t squared plus 10 times A plus delta t minus negative 1.62 times a squared plus 10 times a, all over delta t. So now we need to do some algebra in the numerator, and we'll start by using the distributive property in h of a plus delta t, and just multiplying out h of a. So here we go. So we've got the limit as delta t goes to 0 of negative 1.62 times a squared plus 2a delta t plus delta t squared plus 10 times a plus 10 times delta t plus 1.62a squared. That's going to be minus 10a all over delta t. Now let's go ahead and distribute our negative 1.62 coefficient here. So we have the limit as delta t goes to 0 of negative 1.62 a squared minus 3.24 a times delta t minus 1.62 delta t squared plus 10a plus 10 delta t plus 1.62a squared minus 10a. That whole thing, that whole expression over delta t. Now at this point, we can start looking for terms that might add or subtract out. So we've got negative 1.62a and a positive 1.62a. Those will sum to 0. We've got a positive 10a and a negative 10a. Those will sum to 0. And that looks to be about all we can do. So this equals the limit as delta t goes to 0. Now, we do have negative 3.24a delta t and a minus 1.62 delta t squared and a plus 10 delta t that have survived. So we've got negative negative 3.24a delta t minus 1.62 delta t squared plus 10 delta t all over delta t. Now we can factor out a delta t from our numerator. So limit as delta t goes to 0, delta t times negative 3.24a minus 1.62 delta t plus 10 all over delta t. And at this point, my delta t's will divide out. And we're actually at a point now where we can consider the behavior of this function as delta t goes to 0. As a reminder, we could not consider the behavior up until this point because we still had delta t in the denominator, and as delta t goes to 0, that means that denominator is 0. We've now resolved that issue, so we now have the limit as delta t goes to 0 of negative 3.24a minus 1.62 delta t plus 10. And as delta t goes to 0, negative 3.24a will just go to negative 3.24a. Negative 1.62 delta t will go to 0 because 1.62 times numbers that are approaching 0 will approach 0. And then 10. As delta t approaches 0, 10 will continue to approach 10. So what have we discovered? We've discovered that the velocity at t equals a, which is the same as the first derivative of the height at time a, is equal to negative 3.24a plus 10. Now, I'll leave it to you to check that if a is equal to 1, we get the value we found in our previous example.